So yeah, how do you guys feel in general about the cache section and whatnot? Because like there's been a lot of stuff going on, and so if you haven't gotten like a chance to completely work through things, that's totally understandable. So I just want to sort of like gauge how you guys feel. Most of you guys filled out the forms, but in general, it seems like there's still like a lot of stuff about caches to cover. Would you guys rather like do more problem focused things today, or just like talking about caches and conceptual stuff, and then like answering any questions that you guys have and whatnot? So any preferences? Okay, cool. So I'll try to mix there because there are like some people who want to have more conceptual stuff. So I'll try to like work in the conceptual stuff through the problems. I will give like some time to work through like the individual ones, as well as like go through like walk through some of the examples if that works. Okay, cool. We're good in terms of notifications. Okay, so first things first, I'll just talk for a couple minutes about general caches, and as a brief reminder. So what caching is basically like it allows us to access different pieces of data in memory without having to go to main memory every single time. And so that helps us because it's faster, because it's a lot more time efficient, and it allows us to basically access the stuff in a faster manner. So the way in which it works is there's a cache, and so within the cache, based on the type of cache it is, different blocks of memory will get placed into the caches, and then so based on the offset given by the address, so it's the like X number of bits at the right least significant bits, it'll tell us where to read from that chunk. And then so the index, which is the middle section of bits, it tells us which like cache line that we're going to fill it with. And then so the tag bits at the very beginning, they're the ones that tell us basically whether two blocks that have the same index are equal or not. So it allows us to differentiate between the types of caches and such, or this type of cache lines and whatnot. And then there's also a couple of there's also a couple of other things that come with caches. So because caches aren't as large as main memory, basically there's going to be an eviction policy. And so the ones that's typically going to be used is LRU, which is least recently used. It just means that the oldest item that hasn't been accessed in the cache will be the first one evicted when we have to load something else new into the cache. Another concept is like the idea of misses. And so there are three main types of misses that we're focusing on right now. You'll notice that later on, there'll be 4 types of misses, and the last one of which is coherency. The 3 that we're focusing on right now is like, as we see on the screen, the compulsory, conflict, and capacity misses. These are the 3 that we want to focus on for now. So just really quickly to go through things. Okay, let me see if my pen has finally connected. So for the very first one, what we have is our compulsory. And so that in particular is basically unavoidable in most circumstances, in non-ideal circumstances, basically. So the idea of that is that the first time we're accessing a particular block, regardless of what the state of the cache is, it will basically happen regardless. So this is going to happen. The cause is first time a memory block is accessed no matter what. This formatting is kind of whack. I would actually just number this and like write it out in the margins, but this is one. The solution for this is technically like NA. There's really no real solution. It's kind of unavoidable, but it's actually sort of like you can ameliorate, you can make it a little bit better, and in a perfect theoretical sense, you can avoid it by doing basically preemptive loading. So this is something that you'll see in the discussion sheets. This is mildly outdated, but basically the idea of preemptive loading is like the idea of branch prediction, like doing branches and doing jumps. Like you can try to predict like what your next lines are going to be. So, and they'll just flush it if it's wrong. So similarly for this is like before a cache actually warms up, or like like after a particular access, it'll try to predict the next couple of accesses that'll happen. Like for example, if it feels like, so like so far you've accessed every consecutive block because you're like going through a loop or something, it'll try to decide, oh, well, I'm going to load these blocks in advance. So like the next 2 blocks, and then hopefully it'll end up being a hit. If it's not, well, I've just loaded it. So it's going to be a little bit of an overhead. But if we do actually, if it succeeds, then what it means is that basically we'll have preemptively loaded it while an old access is happening, which means that it takes less time overall, but allows us to essentially avoid having the miss and then go into the hardware memory and then, or main memory, and then use that as extra time. So that's the idea of preemptive loading. The answer key that I'll send out after this will wind up being basically there's no solution, but there technically is. For the second one, types of the conflict miss, we're going to make this pink just to give it a little differentiation. A conflict miss is when two addresses have the same index. So what this means is that basically, if you have a particular an address and you break it down with the TIO like breakdown thing, which we'll talk about a little bit about later, if the index portion is the same, then it means that it maps to the same set in memory. So if we have a direct mapped cache, so basically a direct mapped cache, another way of saying it is a one-way set associative. So a direct mapped cache is basically the same thing as one-way set associative. Set associative. The idea behind that is basically for every single index, there's only going to be one block in cache that can be associated with that index. So this can go up to basically n-way set associative. So n-way set associative. And what this is referring to is basically that at this point, for every index that you have, there's going to be n blocks that can be fit in here. So the reason that this is important is because with direct map cache, it means that there's only one block that can go here. So if you jump by like a cache size, like a jump like that, then what's going to happen is the next address that you access is necessarily going to have the same index, which means that even if the rest of the cache is empty, it's going to kick out the old one and then in that position and then load this new one. But then if you try to go back and access something there, because it goes in the same position, it's just going to switch back and forth. So it becomes really inefficient. So increasing the associativity helps reduce the conflict misses, which is the type of miss that we just talked about. It's when basically you miss something and then you have to replace it because there's a conflict of indices. So this happens when two blocks have the same index or indices, aka maps. Maps to same set. And then you solve this by increasing associativity. So the most that you can get is, and winds up being, the highest is winds up being a fully associative cache. So what fully associative means is just however many blocks you can fit in the associative cache. So what this means is like however large your cache is, so however number of blocks you can fit, that's going to be what's the cache number is. Are there any questions so far? Okay. Okay, so for the last one, what we have is a capacity miss. So we're going to use orange for this. Capacity basically means that there's no more space, cache is full. So basically you tell this by not necessarily checking for like if it's less than fully associative, because like if it's less than fully associative, it doesn't matter if the cache is full or not. You can always have a miss otherwise. But if it's a fully associative cache, then you're going to basically know that, well, any miss that I have that's not a compulsory miss is going to be because I can't fit it into the cache itself. So the only way that we can solve this is basically by increasing size of cache. So, okay, are there any questions? Okay. Let me know if I'm going too slow or too fast or anything of that sort, if you want me to change up or anything. So we're gonna take a, so there's really no problems associated with this. At this point, I would say like the main type of problems that we're gonna see is like later on when you're analyzing code and looking at it like in the homework, where it's saying, okay, for this code and for these cache specifications, what are our hit rates and miss rates gonna be? So just a quick thing, the hit rate is, so hit rate or HR is going to be number of hits divided by the number of accesses. So you'll see in discussion that there are going to be global and local hit rates. And basically that's just talking about multi-level caching and multi-level page tables and whatnot. And the difference between that is basically saying, okay, for each level of the cache, how many hits do I have? And then so based on that, then we have our, so for a global, what it's going to have is number of, let's say this is like miss rate for number of misses at the cache level. So like, for example, if I have 2 level caches, for the first level, I have like 10 misses. For the second level, only 5 go through. So like, oh, so we have 10 misses. So that means 10 accesses go through to the second level. And then in the second level, we have 5 misses. So for the second level, we will have 5 misses. For the first one, we'll have 10. So then we divide that by the number of overall cache accesses. Whereas for local hit rate, it's going to be slightly different. So, well, oops. So let's see, for here we have local, and the local hit rate is the total number of misses at the particular cache level divided by the number of cache accesses at the cache level.
Quick question for global. Yeah. Is it not like, so when you say number of misses at cache level, like which cache level? Or do you mean like all cache levels?
I mean like at the cache level that they're specifying. So they'll specify either like overall, in which case then you'll only count overall, and that's when things might get like double counted, like you'll see in lab. But for like specific levels, it'll say, okay, so for this particular cache, what's the global miss rate?
Okay.
Does that make sense?
Yeah.
Okay, cool. Are there any other questions about like this whole missing and hit rate and all of these like things? Okay. If they're not, I am going to tentatively for now. Do you guys want me to cover briefly like a TIO breakdown and whatnot? Or no preference? Okay, so I'll briefly cover this, and then we're gonna actually not like work on some of the problems. We're gonna jump to the multi-level page caching kind of thing, so that way we'll be able to kill 2 birds with 1 stone. So briefly, just to break down the idea of TIO, breakdown. TIO stands for, like you said earlier, tag, index, and offset. So tag, index, and offset. So what each of these refer to is it allows us to parse the instruction, or not the instruction, the address in a very specific way that causes us to understand like, oh, based on this instruction, or sorry, I keep saying instruction, based on this address, you'll be able to tell where a block got loaded from, where it's sitting in the cache, and what state that it has, and like where the data is. So this TIO breakdown is for the address, for an address. So which means that if you get a hex address, basically you'll be able to break down. I don't know why, wait, I'm really confused. This is not really responding. Okay. So the way in which we break it down is first things first. So I always like to start from the offset. So what the offset specifies is how far or what index is the data I want sitting in for the block. So what this means is like you'll load a particular block and it'll be a certain size. And so let's say it's a 32 byte block. So that means we're going to start with index 0 and go all the way up to index 31. So that means if you want, for example, byte 17, so the 17th byte, or then we want to have an offset of 16s because we're zero indexing. So this allows us to basically go into the block and be like, okay, this is the byte that I'm looking for. So it allows us to actually access the direct data. So on the other hand, the index, what it does is it tells us which set a given address or a given block is sitting. So it tells us which set a block of data is sitting in. So the way in which we would want to find this is basically, what we're trying to do here is, well, our cache is a specific size. And then in order to figure out how many blocks are actually in this cache, we're going to do cache size divided by block size. That gives us the number of blocks. Now, because we will have a specific set size, like two-way set associated by so like we have a set size of 2. So in order to figure out the number of sets that we have, we want to divide it by the set size. So once we have the total number of sets, to understand how many bits that we need to represent that, we have to take log 2 of that because every bit can represent 2 states. So the overall way that you do this would be log 2 of cache size divided by block size times n, which is n being the set number. So like an n-way set associated of n being the however many blocks per set. Just really quickly for offset, the way in which you figure that out and the number of bits needed to represent the offset is log 2 of the block size. And the reason for that is just because, like we said earlier, the bits can represent 2 states for everything. So to figure out the total number of states would be 2 to the n, so vice versa would be log base 2 of n. The tag bit, like we said earlier, is used to identify. So used to ID, used to identify the specific block when index is the same. So this allows us basically to differentiate between different blocks that get loaded that wind up having a conflict miss, because at some point, like if all we see, like in terms of the regular values, is the index, which is the location, and then the offset, we really can't differentiate anything because multiple blocks could have those values. But in order to differentiate it, basically we take the tag bits, which are stored elsewhere, and we say, okay, well, for this particular block, this is our tag bits. If these tag bits are different, then it's going to be a different block. Just as a quick forward, the caches that we're talking about are only going to be storing the data, so it's just the data caches. The tag bits, because they're not included within this section, they're stored elsewhere. So it's basically we have to compare based on a specific sector for that. So to figure out this, if we have a 4 KB cache, 256 block size, and we have direct map. So if we have our block size of this, that means we need 8. This is 2 to the 8 bytes. So that means we need 8 bits to represent the offset. So this is for offset. And then to figure out the number of pages, what we need is, let's see. So if we have a 16-bit system, in order to figure out this, if it's direct mapped, that means we know that n is going to be equal to 1. So that means to figure out our index, so I is going to be equal to log base 2 of our cache size, which so 4 KB bits is going to be 2 to the 12 bytes. This is IEC indexing or IEC prefixing, so 2 to the 12 right here, divided by 2 to the 8 of the page size times 1. And so now you see why we use IEC prefixes, because that way it allows us to work with the values in a much simpler fashion. So this gives us log base 2 of 2 to the 4. So we need 4 bits to represent the index. And then so if everything else can be given to the tag bits, sorry. So overall, the way that the breakdown is going to look is something along the lines of this. So we have 4 bits. Can I do math? Yes, I can do math. So 4 and a 4 and 8. So that's how it's going to break down. So those are going to be 0 to 7, 8 to 11, and then 12 to 15 in terms of indices for the bits. Are there any questions for this section? So let me zoom out a little. give you a little bit time to sort of absorb all that. Are we good to move on? Are there any questions? Okay, so I'm gonna briefly move on. So we're gonna jump actually. Right here we'll see like we have some missing and whatnot. So we'll come back to this later if we have the time. But right now what we're going to talk about is multi-level caches, and this is slightly different, but also still very similar to what we've already covered. So the way that multi-level kind of paging, or not paging, sorry, caches work is that like there are certain sections that get portioned out for specific like ways in which like they get categorized, and so these are actually going to be like broken down very similarly. So I'm going to give you guys a couple minutes to work through so 3.1, I'm going to give you guys about 3 minutes to work through this to do the TIO breakdown and figure out which like indices the different breakdowns occur at. And then we're going to talk about 3.2 after that. So if you guys finish early, you can definitely go through and look at 3.2. So I'm going to like zoom out a little bit. Probably another minute or so. Okay, so I'm gonna oops, I'm getting really loud. I'm gonna start going over the answers to this. This is right now, it's not multi-level caching, so I'm gonna just go through it kind of quickly. So let me know if you guys want me to repeat anything or go into anything into more detail. I kind of want to get to the multi-level part of this because it's quite interesting, and it'll be really applicable as well for the virtual memory portion of this class. Okay, so a couple of things. First things that we have to notice first that this is an 8-way set associative cache, so our n is going to be equal to 8. We have 212 bytes of data, so that's just that by for itself. For each block is 16 bytes. That means we're going to be using that to figure out our offset. And we have 8 MB of main memory. So you notice like oftentimes when we talk about memory, it'll be in the IEC prefixes. version. So I would highly recommend, if you don't feel comfortable with it, to review that and just do some basic conversions. Discussion 1 actually has all of those conversion practice things. So if you want practice going between the two, I would say look at discussion 1, not worksheet 1, discussion 1. Okay, so to figure this out, first what we have is, oops. So we want to figure out our offset. So our offset is going to be log base 2 of 16, which is 2 to the 4. So that's going to give us 4 bits worth. So then for our index, what we have is, well, we have our 512 bytes of data for the set associative cache. So we have log base 2, and then we have 512, which is going to be 2 to the 9, divided by our each block size, so 2 to the 4. And then we have an 8-weight set associative cache, which is 2 to the 3rd. So that's going to give us, divided by, this is 7, so we're going to be left with log base 2 of 2 to the 2. So that's going to give us 2 bits for our indices. And then so that means our tag bits are going to be everything that's left. So we have, let's see, if we have 8 MB of main memory, our main memory size is going to be then 2 to the 3rd, which is 8, times 2 to the 20, which is the MB part. So that's going to give us 2 to the 23rd overall bytes of memory that we can access. And because memory in 61C is always going to be byte address, that means we can we're going to be able to access it with 23 bits overall. So to actually get our tag bits, we'll have 23 minus 2 minus 4, which is going to give us 17 bits for our overall tag bits. So our final answers are going to be 4 for offset, 2 for the index, and then 17 for the tag bits. Are there any questions for this part?
So we will always use like the main memory size to determine how larger addresses are, right?
Yeah.
Okay.
Yeah, just a really quick reminder as to why. The reason is because memory addresses, what they're trying to do is basically like index our memory. So because we're byte addressing, which means that like every index is going to correspond to a byte in memory. That means for every byte, like however many bytes that we have, we're going to have a unique index. And the index in this case is basically that it's just the address. It's just another name for indexing. Okay, so if there are no questions, I'm going to move on to the second one. I'm just going to talk a little bit about this before actually I try the problem. So here we have 2 caches, L1 and L2. Level L1 is referring to level 1, so it's always the first level cache that you hit first. And then L2 is the second level. So if you miss on the first level, then the misses transfer to the second level and they check out the misses in order to determine whether there's the data is there or not. So both caches are direct mapped. So both caches have an n equals 1. And then L1 cache can hold 256 bytes of data. L2 cache can hold 4 KB. So as you can see, the lower the cache level, the larger it is. And the reason for that is because the less expensive it becomes. So having the higher level things like registers, as we know, are incredibly expensive because they're basically holding their direct things, and they're super, super fast, but they're super expensive, which is why we don't have an entire memory sector made out of registers. Then like thinking about caches, because it's faster than main memory, the higher the cache, the faster it is, but also the more expensive it is, which is why it's limited in size. But that's also why it means that we can like sort of offset the number of like differences we have between the main memory and the caches by adding more cache levels. Okay, so we have assume the following code is run on this machine, yada, yada, whatever. This produces a hit rate of 7 out of 6 for the L1 cache. So that means 7 hits in 8 accesses in L1. And then for L2, it's going to be, so if we think about it similarly, 6 hits per 8 accesses. Given that array is a block aligned address, and so which means that like basically we're going to assume that basically 0 is our index of 0 is going to be the start of a block. And size of uint16t is 2 because it's 2 bytes. What is the block size of what is the block size of L1 cache in bytes that produces this hit rate? So, and then for the second one, we have use the variable y to represent the answer in part A. So it doesn't matter what we got in part A. What is the block size of the L2 cache in bytes that produces L2's hit rate? So express your answer as a function of y, not as a single number. So I would say a couple of tips to start approaching this is to first analyze the for loop to see what it's actually doing. And then so how many accesses do you have per loop? How are we jumping throughout the loop? How many accesses are we trying to get for a certain number, or how many hits are we trying to get for a certain number of accesses? What's going to cause a hit? What's going to cause a miss? Things like that. So that's how I would approach this problem initially. I'm going to give you guys about 3 to 4 minutes to work on this so far, and then we'll reevaluate at the end of that to see if we need more time. Does that sound good? Okay. So I'm going to zoom out just a little bit so you guys can see. I'll be back in about 30 seconds. I need to pour a little bit of water. Probably another minute or so. Do you guys feel like you're ready or you feel ready to go over the answers, or do you guys want a couple more minutes? Okay, I'm gonna go over so we can talk a little bit about other stuff and answer anything else that you might have for questions. Okay, so going over this one, there's a couple of things, first of all, that we want to keep in mind for all of this. So when we're looking initially at these questions, what we want to first identify is, well, how many total accesses do we actually have? And so for all of this, going into the actual part, so the only time we actually access index into the array is on this line. So when we have total plus equals array at 1. So this is going to be just one access. So that, and then looking at inside the loop, there's nothing else. So we're only going to have one access per loop run. So that means that in order to have 8 accesses, which is like what we're looking at for L1 cache, we want to have basically 8 loop runs, 8 loops. So going off of this, then that means we're going to have 7 hits in 8 accesses. So what this implies is for every 8 accesses, it's most likely going to be the first access that's going to be a miss, because it'll be a compulsory miss, because whatever block that we're trying to access is probably going to be fresh. So basically what we wind up having then is, we know, well, that means we load one block, and for one block, we'll be able to access it 8 times. So looking at how this actually works then, because we know that the items that we're accessing in the array are UINT16Ts, which are 2 bytes given the problem specs, we know that 8 accesses will be 8 different values for this in the array. So that means our total block size is going to be 2 times 8, which is 16 bytes for L1. Are there any questions for this?
What about like, so I guess like, how do we know that it's like 8 and not something more, and still the hit rate is 7/8?
Wait,
Or
can you
do we not?
repeat the question?
Oh,
Sorry.
sorry.
Oh no,
So
part of
like,
it cut out. My internet's kind of wonky.
so like, I guess how do we know that it's there are 8 loops? Because like, what if there are more but just a fraction of 7 over 8? Or like, does that not matter?
Yeah, so that's a great question. It doesn't actually matter, because what we're focused on is we want to figure out what this ratio is referring to. So like this ratio is talking about for every 8 accesses, we're going to have 7 hits. So that means for every single like cycle of 8,
Okay.
7 hits. So that's why we're only focused on 8 loops here. Like the array size can be whatever, but we know that for every 8 will have a miss.
Okay.
Are there any other questions for this part? Okay, if not, I'm going to briefly talk about part 2, which is quite similar, but there's just a small trick to it. So for this one, most of it is going to be the same. The only difference is that we're actually going to have a slightly different way of looking about it. And the reason for this is because there are 2 things that happen. First of all, the access pattern for this winds up being 3/4, which it means we have, for every 4 accesses, we're going to have 3 hits. So that means for the for every 4 accesses, the first one will not be in L2. So that means we'll have to go into main memory for that. But something else that's going to be different is for every block that we load into L1 is also going to be loaded into L2, which means that also, to a certain extent, our block size like in L2 is going to be different. So in order to actually accomplish this, what we know a couple of things. The first thing that we know, in addition to everything else, is that only misses in L1 go to L2. And the reason is because, well, if we have a hit in L1, we don't need to go to another level and spend more time like trying to find that. So that means we know that from this, we're going to have 1 visit to L2 every 16 bytes. And the reason for this is because it comes from the first one. So like looking at this, using y to represent this, well, this is going to be y. So which means that in order to have 4 accesses, we must have 4 times y bytes overall for the block. And because the reason that this is the case is because, well, if we have individual blocks, then every axis is going to be a miss, because we're going to have 1 axis every 16. for every y. So computing this overall, it's going to wind up being a 64 byte block instead. Are there any questions for this section? Okay, if there okay, just like as a quick kind of like sanity check-in, how are you guys feeling overall about like these concepts that we talked about? Okay, thumbs up, I guess, like on your screen if you feel good. Yeah, okay. That sounds great. We're gonna spend, so we have about 7 minutes left. Would you guys rather spend it working through some like miss questions or like types of misses and whatnot, or would you rather go over AMAT, so average memory access time? Or no preference, in which case then we'll talk about AMAT. Okay. Okay, cool. I think I'm gonna briefly talk about this part just because it's like a slightly different. It also has to do with like these last two questions. So I'm gonna talk briefly about that and then come back here. So okay. So the idea of AMAT is basically we can't actually decipher like, oh, if we say, oh, for this particular system, what's going to be the time that it takes to access memory or like to do this one access? And we can't really say because it could be in the L1 cache, it could be an L2 cache, it could be an L3. If your computer is just that fancy and has L4 caches, like it could take that long. It could also have to go to main memory. It could also have time to go to the disk. So the general formula in which that you would want to calculate this is just, let me write it over here. So general AMAT time is going to be the hit time. I'll just write it with hit HT, and then plus the miss rate of whatever level you're on times the miss penalty, so MP. So MP, it can kind of like recurse in the same format, the same format for as many levels as you have. So what this means is basically if you have one level, then this is what the MP, like one level is just going to be like time like L1 miss time or something like that, like how long it takes to access main memory. And then like you'll continuously go down. Like for example, if you have two levels, then what will wind up happening is like then within like MP, it's going to equal, well, L2 hit time plus L2 miss rate times the L2 miss penalty. Sorry. And so like it'll keep on going like this. So keeping that in mind, I'm going to give you guys about, so we have 5 minutes left. I'm going to give you guys about 3-ish minutes to work through these two. And then we'll briefly go over the answers as well as any questions that you guys might have. Oh, phone died. It's probably another minute or so on this.
Questions can pop up anytime.
I love advertisements. So probably another 30 seconds or so of this. Okay, I'm gonna just spend the last 2 minutes talking through some of this stuff and anything else that you guys might have questions on. So yeah, if you guys have any other questions about anything else, drop in the chat and I'll answer towards the end. But I'm just gonna briefly talk through these two right now. So to calculate EMAT, so like these are like decently straightforward in terms of like what the different kind of misses are, but they're very indicative of problems that you might see with regards to this, because like, to be honest, you can't really get too complicated with this, especially in 61C. So if you feel like you understand these, then you're on a really good track to go for it. If you feel a little confused, that's totally okay. That's what these practice problems are for. Okay, so considering the following cache setup, we have an L2 or L1 cache with a hit time of 2 cycles. So like you'll notice, we'll be talking about everything in terms of cycles as opposed to actual time. L2 cache with a hit time of 18 cycles, so how long it takes to access it, and a 15% local miss rate and a global miss rate of 5%. If main memory accesses take 60 cycles, what is the AMAT for the caching hierarchy in terms of clock cycles? So the way in which we want to calculate this, so this is with regards to L1. The reason is because with L2, what's going to happen is then it will allow us, so basically any misses that you'll have will wind up being overall anyway. So like if we take a look at this, our L1 miss rate will look something like this. So our L1 miss rate will look like the local or the global miss rate divided by the local miss rate. And the reason is because if we look at the previous equations that we have for this, so somewhere back here, if we divide the two, so like divide global by local, then we'll have what we'll wind up having is this divided by this. And then so that will allow us to get us the overall amount of misses that we wind up having, because the only ones that have to go on to the next level are going to be the ones that miss in L1. So then if we get this, then the value that we wind up getting is going to be 1/3. So then kind of going through this, then what we have is, well, our AMAT's going to be structured in this way. So our AMAT's going to have L1 hit rate, which is, or hit time, which is going to be 2 cycles. And then we're going to have 1/3, which is going to be the L1 miss rate. So I'll mark this using. So 1/3, and then we're going to have, well, now we need to have the L2 time hit rate. So we're going to have 18 in here, and then we're going to add it, sorry, I can't speak. We're going to plus the local miss rate, because we don't want to have global, because we're only looking at the number of accesses that go into L2. So that's why we use the local miss rate for this. So that's going to be 0.15 times the penalty for missing in L2, which is going to wind up being going to main memory. So it's going to be 60 right here. So then what's that's going to be is 2 plus 6 plus 5/100 times 60. And then so that's going to give us 8. And then this is going to give us something in the realm of, let's see, this is 30/10. So this is going to give us 3. And so that's going to give us a total of 11 cycles. So for our AMAT. Are there any questions for this? Okay. Are there any other questions overall, just like in general about caching and whatnot and the like that you guys would like answered? Okay, if there are not, then I'm gonna end the recording now. And technically, because we're a little bit over time, I'll let you guys go so you can enjoy your Saturday and do whatever work you need. But yeah, if you, like always, if you guys have anything that you want to talk about, anything, feel free to email me. And yeah, elections results are out, so hopefully everyone's decently happy about that, but no more stress about election wise. And yeah, have a good weekend, guys.